Hello, welcome to my channel. In this video, we are going to be taking a look at problem under inclined plane. And the problem we want to solve has a diagram of this form. So the question that can come out of this diagram has this statement that we have a solid sphere and a solid cylinder. Both of them have the same mass and the same radius. So the question is, which of them will get to the bottom first? To solve this problem, we have two ways of solving it. So we look at the first method. The first method is to find the velocity with which these two objects get to this bottom. So the one with the highest velocity when they get to this bottom will be the one that will get to this bottom first. We can also look at it, calculating the acceleration, which is the second method. So if you calculate the acceleration of both objects and the one with the highest acceleration, then we can conclude that the one with the highest acceleration will get to the floor first. So let's consider the one with the first problem, which is computing their velocity at this point. So we use the conservation of energy formula, which is kinetic energy plus potential energy at point 1, kinetic energy and potential energy at point 2. So we notice that the kinetic energy at point 1 is 0 because they are stationary at that point, while the potential energy is given as the mass times g times h, which is a popular formula for potential energy. Then when they get to this point, at the point when they got to this point, the potential energy will be 0 because the height there is 0. Then the kinetic energy for both, because it involves rolling and translational kinetic energy. So we'll split our kinetic energy into two. So this is what we have. The kinetic energy 0, the potential energy at point 1 mgh equal to the kinetic energy, because this kinetic energy will be split into two, rotational kinetic energy and translational kinetic energy, while the potential energy at that point 2 is 0. So let's see the expression for kinetic energy, the rotational kinetic energy and translational kinetic energy. And we have mgh equal to half of moment of inertia angular times the angular velocity squared plus half of mv squared, right? Okay, so let's see. The next thing is to consider factorize the half out, mgh half, and have this expression. So we can now say what is the moment of inertia for the solid sphere and the solid cylinder. We have the cylinder as half of mr squared and that of the sphere as 2 over 5 mr squared. Now we can combine these two stuff and solve them using one approach. So what we can do is to assume that this particular expression here, half here, is a constant k. So this one is a constant k. So that because this one have mr squared and mr squared. So by the time we replace this one with k and this one with k, we can use one method, one solution to tackle these two problems. So by the time we substitute the value of I into this expression, we have our half kmr squared. So k, when it is 2 over 5, it is for sphere. When it is half, it is for the solid cylinder. Remember, our w here is v squared over r, right? So r squared takes care of r squared, and we have mgh equal to half of kmv squared plus mv squared. We can factorize our mv squared out, and we have half of mv squared k plus 1. We can take care of our m and send these two to this part, and we have 2gh equal to v squared k plus 1. Then we can make our v the Soviet formula. We'll have v equal to the square root of 2gh all over k plus 1. At this point, we realize that the value of k here for any of those two objects determines the value of v. So the smaller this value, the higher the velocity. The higher this value, the smaller the velocity. So between 1 over 2 for cylinder and 2 over 5 of a solid sphere, which of them is smaller? We notice that 2 over 5 is smaller than 1 over 2. So that means the sphere will have the highest velocity, and with this, the sphere will get to the bottom first before the cylinder, the solid cylinder. Okay, so let's look at the second approach. The second approach is to calculate the acceleration of the system. So we consider the diagram in this form. There are two forces acting along this direction, So the first one is the mg sine theta. Second one is the frictional force. So if we resolve this particular equation, it gives us mg sine theta minus the frictional force must be equal to mass times acceleration, right? Now let's see how we can get our F. Remember that our F is the force that causes this particular stuff to rotate. It is a force. So we can find the torque that causes this particular stuff to rotate, and that is giving us the summation of the torque must be equal to moment of inertia times the angular acceleration, where our torque, the only force that is causing this stuff to rotate, is the frictional force. And we bring in our F times the radius of this, either the sphere or the cylinder. We can make F the Soviet formula, or we can add, make the I kmr squared as usual, then times our alpha here, which is angular acceleration, is the tangential acceleration all over the radius. So r cancels r, this r cancels this r, and we make our F the Soviet formula, and that gives us F equal to km times A, which is kma. Remember, r takes care of r, this r takes care of this r, we are left with kma, which is kma. So wherever we see our F, we replace with kma in this equation. So we have mg sine theta minus kma equal to ma. If this one comes to this side, we have g sine theta minus k. Okay, we took care of our m, and we have the next line is a plus ka. We can factorize a out, and we have a 1 plus k, and make a the Soviet formula. We have a equal to g sine theta all over 1 plus k. So at this point, we notice that the smaller the k, the higher the acceleration. The higher the value of k, the smaller the a. And between the solid sphere and the solid cylinder, the solid sphere has a lower constant, which is 2 over 5. 2 over 5 is lesser than that of 1 over 5. So we can say that the solid sphere will get to the bottom before the solid cylinder. I hope this helps. Please like, share, and subscribe.